Alright, so we want to look into which matrices are diagonalizable. Okay, so if A is n by n matrix and it's got n distinct eigenvalues, lambda 1, lambda 2, all the way to lambda n, and they corresponding to eigenvectors v1, v2, and then vn. Then, based on what we saw before, we can write A as P dP inverse, where P is the matrix with columns being the eigenvectors, and D is the diagonal matrix with diagonals being eigenvalues. Okay. So here's our first theorem. So the first theorem is if A has n distinct eigenvalues, then A is diagonalizable, which means it has a diagonalization. But here arises another question, because in the diagonalization, P inverse pops in here, so we need to make sure P is invertible, which means the column vectors are linearly independent. Okay. So for this theorem to hold, we need to prove another theorem first. Let's move up. Okay, so this theorem says that if v1, v2, vk are eigenvectors with corresponding eigenvalues, lambda 1, lambda 2, lambda k, and these are distinct, then v1, v2, vk are linearly independent. Okay. So to cut down the proof, let's just prove the case k equal to 3, and the proof for larger k is similar, but k equal to 3 is easier to see. So suppose we have 3 eigenvectors corresponding to 3 distinct eigenvalues. This means a v1 equals to lambda 1 v1, a v2 equal to lambda 2 v2, a v3 equal to lambda 3 v3. Okay, so we want to show they're linearly independent, so let's assume c1 v1 plus c2 v2 plus c3 v3 equal to 0. So let me write down that thing again. Let's multiply by a on both sides. So let's multiply by a on both sides. Okay. The right hand side, a times 0 is just 0. The left hand side, a times v1 is lambda v1, a times lambda v2 is lambda v2, a times v3 is lambda v3. So we get c1 lambda 1 v1 plus c2 lambda 2 v2 plus c3 lambda 3 v3 equal to 0. And we do the same thing again, so let me copy down that equation. So c1 lambda 1 v1 plus c2 lambda 2 v2 plus c3 lambda 3 v3 equal to 0. Let's multiply by a again. And we get, so same thing, right hand side is still 0 because anything times the 0 vector is 0. Left hand side, AV1 is again lambda V1. So now we get another lambda, so it'll be C1 times lambda square, lambda 1 square V1 plus C2 times lambda 2 square V2 plus C3 lambda 3 square V3 equal to 0. Okay, so let's move this up. So we get a system of 3 equations. We get C1 V1 plus C2 V2 C3 V3 equal to 0. C1 lambda 1 V1 plus C2 lambda 2 V2 plus C3 lambda 3 V3 equal to 0. And C1 lambda 1 square V1 plus C2 lambda 2 square V2 plus C3 lambda 3 V3 equal to 0 square here. So the key is if you do row operations here to remove C1, C2, and C3, you're gonna get is eventually is C1 times lambda 1 minus lambda 2 times lambda 1 minus lambda 3 V1 equal to 0, and C2 times lambda 2 minus lambda 1 times lambda 2 minus lambda 3 times V2 equal to 0, C3 times lambda 3 minus lambda 1 times lambda 3 minus lambda 2 times V3 equal to 0. So now it's the time to use the assumption that lambda 1, lambda 2, lambda 3 are different, because lambda 1, lambda 2, lambda 3 are distinct. This means the difference is not 0. So all these big terms here are not 0. Okay. So we have an equation here, C1 times a non-zero constant times V1 equal to 0. We also know that V1, V2, V3 also not 0 because they are eigenvectors. So the only possibility is that C1, C2, C3 are 0. So therefore, the vectors, eigenvectors, are linearly independent. Okay, so let's recap what happened in this slide. So we have two theorems here. The theorem we prove later, which means if v1, v2, vk are eigenvectors corresponding to distinct eigenvalues, then they are independent. And this theorem implies the first theorem in this video, which says if A has n by n distinct eigenvalues, then A is diagonalizable, where A equals to PDP inverse, and P is the matrix with columns being the eigenvectors, and D is the diagonal matrix with diagonal entries being the eigenvalues.